What if everything we see in the universe, the stars, the galaxies, the swirling cosmic webs, is just a fraction of what's actually out there? Hidden in the shadows, invisible to our most powerful telescopes, lies a force so vast it shapes the very fabric of space itself. This is dark matter, the universe's best-kept secret, a ghostly presence that makes up more than 80% of all matter, yet refuses to reveal its true nature. We've spent decades chasing its shadow, piecing together clues from the way galaxies spin too fast, from the way light bends around nothing, from the way the cosmos whispers its name in the silence between stars. And still, it slips through our fingers like smoke. But what if we told you that dark matter isn't just a single mystery? It's a web of 25 cosmic puzzles, each more tantalizing than the last. Somewhere in those enigmas lies the answer to why our universe looks the way it does, why galaxies cluster into vast, intricate structures, why the cosmos expands at breakneck speeds, and perhaps even why we exist at all. Picture a cosmic detective story where every clue we uncover only deepens the intrigue. From bizarre particles that might be hiding in plain sight to colossal filaments of dark matter stretching across billions of light years, this is a journey into the unknown where the rules of physics as we know them might not even apply. So let's step into the dark together. Forget what you think you know about the universe, because what lies ahead will challenge everything. We're about to unravel 25 of the most mind-bending mysteries tied to this invisible cosmic architect, each one a piece of the puzzle, each one a story waiting to be told. By the end, you might just see the night sky differently, because out there in the void, something is watching, and it's been shaping our reality since the dawn of time. Think of the universe as a grand cathedral, one whose walls and arches aren't made of stone, but of something far stranger. Dark matter is the invisible architect, weaving an intricate scaffold that holds everything together. Without it, galaxies would fly apart, cosmic structures would crumble, and the night sky as we know it would vanish. This isn't just some background player, it's the hidden force that carved the universe into the shape we see today. Take a galaxy like our Milky Way. Stars on its outer edges whirl so fast that, by all known laws of physics, they should be flung into the void, but they aren't. Something unseen, an enormous halo of dark matter, wraps around the galaxy like a gravitational embrace, keeping it intact. And it's not just individual galaxies. Zoom out far enough and you'll see dark matter's grandest masterpiece, the cosmic web. Stretching billions of light years, this vast network of filaments connects galaxies like beads on a string, with dense knots where galaxy clusters collide and merge. Here's where it gets eerie. When astronomers map this web, they're not seeing the dark matter itself, they're tracing its shadow. Like fog bending the beam of a distant lighthouse, dark matter warps the path of light from galaxies behind it, a phenomenon called gravitational lensing. These distortions reveal ghostly bridges of matter where nothing visible exists. It's as if we're decoding the blueprint of a building we can't enter, guided only by the way light dances around its edges. But why call it scaffolding? Because without dark matter's gravitational pull, the universe would lack the structure for stars, planets, or even us to exist. In the early cosmos, tiny ripples in dark matter acted like seeds, drawing in gas and dust to form the first galaxies. It's the reason we're here, the reason anything is. And yet, for all its power, dark matter remains frustratingly elusive. It doesn't reflect light, absorb it, or emit it. We only know it's there because the universe moves in ways that defy explanation. So the next time you look up at the night sky, remember, what you're seeing is just the glittering surface. Beneath it lies an unseen architecture, vast and mysterious, holding the cosmos together thread by thread. If dark matter makes up most of the universe's mass, why does it hide in plain sight? Unlike stars, gas, or even black holes, dark matter refuses to glow, reflect, or flicker. It's the ultimate cosmic ghost. But this invisibility isn't just a quirk, it's a fundamental clue about what dark matter might be. Take ordinary matter, the atoms in your body, the light from your screen. It interacts with light because of charged particles like electrons. When light hits an electron, it can bounce off, get absorbed, or re-emitted, creating the visible world. But dark matter plays by different rules. Theorists think it might be made of particles that don't carry an electric charge at all, rendering them blind to light's touch. Imagine trying to see a shadow in a pitch-black room. It's not just dark, it's fundamentally disconnected from light itself. This brings us to two leading suspects, WIMP and actions. Weakly interacting massive particles, or WIMP, are heavy, sluggish particles that barely interact with anything, passing through planets like they're not even there. Then there are actions, ultra-lightweight particles so tiny they behave more like waves than solid matter. Both could explain dark matter's silence, but here's the catch: we've never directly detected either. The hunt for these particles reads like a spy thriller. Deep underground, in abandoned mines and beneath mountains, scientists have built traps lined with ultra-pure materials, waiting for the faintest tick of a WIMP collision. Meanwhile, other experiments use powerful magnets to coax shy actions into revealing themselves. So far, the detectors remain eerily quiet. Either these particles are even more elusive than we thought, or dark matter is something stranger altogether, a cosmic illusion we're only beginning to unravel. But the mystery runs deeper. Some theories suggest dark matter might not be particles at all, but primordial black holes forged in the universe's first second. Others propose entire hidden sectors of physics where dark matter communicates through forces we've yet to discover. Every dead end in the lab forces us to rethink what's possible, to question whether we're even asking the right questions. One thing's certain: dark matter's invisibility isn't a flaw in the universe, it's a message. The fact that it refuses to shine means it's built from something profoundly alien to everything we know. And that's what makes this puzzle so thrilling. Every failed detection, every quiet experiment pushes us closer to rewriting the rules of reality itself. The universe loves throwing us curveballs, and one of its most baffling comes in the form of missing galaxies. According to our simulations, the Milky Way should be swarming with hundreds, maybe even thousands, of tiny satellite galaxies, each tethered to us by dark matter's invisible grip. But when we look up, only about 60 show up on telescopes. This glaring mismatch, dubbed the missing satellite problem, has haunted astronomers for decades, forcing us to question whether we've misunderstood dark matter's role in shaping the cosmos. Picture a cosmic game of hide and seek. Supercomputer models based on dark matter's behavior predict a bustling neighborhood of dwarf galaxies orbiting giants like ours. These simulations paint a universe where dark matter clumps together, creating gravitational wells that trap gas and spark the birth of small, faint galaxies. But reality tells a different story. The ones we've spotted are mere stragglers, far fewer, far dimmer, and arranged in a vast, flattened plain around the Milky Way, not the scattered swarm our models expect. It's like expecting a bustling city and finding a ghost town instead. So where did the rest go? One possibility cuts straight to the heart of dark matter's nature. Maybe it's colder than we thought. In physics terms, cold, dark matter moves sluggishly, allowing it to clump easily into small structures. But if dark matter were slightly warmer, more energetic, its particles would zip around faster, smoothing out those tiny clumps before galaxies could form. That would explain why we see fewer dwarfs. Yet even this theory doesn't fully account for the odd distribution of the ones we do observe. Then there's the wild card. What if the missing satellites aren't missing? Some could be so faint, so star-poor, they're practically invisible against the blackness of space. Others might have been torn apart by our galaxy's gravity long ago, leaving behind only streams of stars as cryptic evidence. Recent discoveries of ultra-faint dwarfs, some with just a few hundred stars, hint that we're only beginning to scrape the surface of what's out there. But the plot thickens. Even if we find more dwarfs, their bizarre orbits challenge our understanding. Instead of swirling around the Milky Way randomly, many line up along a single plane like planets circling a star. This shouldn't happen in a universe dominated by dark matter's chaotic pull. Could there be another force at play, or could dark matter itself behave in ways we haven't dreamed of yet? Every answer leads to new questions, but that's what makes this mystery so electrifying. The missing satellites aren't just a counting error, they're a cosmic riddle, whispering secrets about the invisible framework of the universe. And with every faint galaxy we spot, we're one step closer to rewriting the story of dark matter itself. Sometimes, to see the invisible, you have to watch the universe tear itself apart. That's exactly what happened with the Bullet Cluster, a pair of galaxy clusters caught in a catastrophic collision 200 million light-years away. This cosmic crash didn't just give us stunning Hubble images, it handed scientists the smoking gun for dark matter's existence. Here's why this event was so revolutionary. When these clusters slammed into each other at millions of miles per hour, their gas, the hot, glowing plasma that makes up most of their visible matter, piled up in the center like traffic in a cosmic fender bender. But something else kept moving unaffected. By mapping the cluster's gravity using gravitational lensing, the way its mass bent light from distant galaxies behind it, researchers found an eerie discrepancy. The bulk of the mass wasn't where the gas stalled. It had sailed right through the collision, trailing behind in two distinct clumps. This was dark matter in action. Unlike the gas, which interacts and slows down, dark matter's ghostly particles barely notice each other. They pass through the wreckage like phantom racers, dragging the cluster's gravity with them. The result, a perfect separation, visible matter glowing in the middle, dark matter lurking on either side. For the first time, we weren't just inferring dark matter's presence from galaxy rotations or cosmic webs, we were seeing its shadow split from ordinary matter in real space. Simulations of the event tell an even wilder story. When scientists recreated the collision in supercomputers, they found the dark matter halos of both clusters behaved like silent specters, barely disturbed by the chaos. Meanwhile, the gas released enough energy to power billions of supernova, creating shock waves that heated it to hundreds of millions of degrees. Yet none of that fury affected the dark matter's path. It was as if two crowds of people collided, but only their clothes got tangled. Their invisible bodies walked right past each other. The Bullet Cluster isn't just proof of dark matter, it's a masterclass in how little we understand it. This stuff doesn't just ignore light, it barely interacts with anything, not even itself. And that raises a haunting question. If dark matter can barrel through a collision of galactic proportions without flinching, what else is it capable of? Could there be entire dark galaxies, dark stars, even dark planets, all hidden in the void? One thing's certain, the Bullet Cluster didn't just confirm dark matter's existence, it showed us how alien it truly is. Out there, in the depths of space, the universe is playing by rules we're only beginning to decode. In the 1970s, astronomer Vera Rubin peered into the heart of a spiral galaxy and found something that shouldn't exist: stars hurtling so fast they defied the laws of gravity. According to Newton's equations, stars on the outer edges of galaxies should slow down as they orbit, just like planets farther from the sun move more sluggishly. Instead, Rubin's observations revealed a cosmic rebellion. No matter how far out you looked, stars whipped around at nearly the same speed. It was as if a ghostly hand were gripping them, refusing to let go. This bizarre behavior gave birth to one of dark matter's most compelling clues: the galaxy rotation curve problem. Picture a merry-go-round where kids on the outer edge somehow spin just as fast as those near the center, despite physics demanding they trail behind. Rubin's data showed rotation curves staying flat as you moved outward, a phenomenon Newton's gravity couldn't explain unless galaxies harbored hidden mass. Lots of it. Calculations revealed that visible stars and gas accounted for barely a fifth of the gravity needed to hold these speeding stars in place. The rest, an invisible halo of dark matter stretching far beyond the galaxy's luminous edge. But here's the twist: dark matter doesn't just fill the gaps, it reshapes our understanding of gravity itself. Alternative theories like modified Newtonian dynamics or MUND suggest gravity works differently on cosmic scales, eliminating the need for dark matter. Yet MUND struggles to explain phenomena like the bullet cluster, where gravity clearly divorces from visible matter. Dark matter, for all its mystery, remains the simplest fix, a cosmic glue holding galaxies together against their own frantic motion. Rubin's discovery wasn't just a breakthrough, it was a wake-up call. The universe wasn't playing by the rules we'd written, and as later studies confirmed her findings in galaxy after galaxy, one truth became undeniable: the cosmos is teeming with something we can't see, can't touch, but without which the night sky would unravel. Every spinning galaxy is a silent testament to dark matter's grip, a reminder that the universe hides its greatest secrets in plain sight. Deep beneath the mountains of Italy, inside a lab shielded from cosmic rays, a detector silently records something strange. The Dama/Libra experiment has been picking up a faint, rhythmic signal for over 2 decades, a pulse that rises and falls with the seasons like a cosmic heartbeat. Scientists behind the project claim it's evidence of dark matter particles streaming through Earth as we orbit the Sun. But here's the catch: no other experiment has ever confirmed it. This tantalizing mystery, known as the Dama anomaly, has split the physics community in half, sparking fierce debates over whether we're glimpsing dark matter's shadow or chasing a phantom. Imagine Earth as a ship sailing through an invisible river. According to some theories, our galaxy swims in vast currents of dark matter, remnants of ancient dwarf galaxies torn apart by gravity. As the Sun moves through the Milky Way, it should drag these streams along with it, creating a wind of particles that changes direction as Earth orbits. Dama detectors filled with sodium iodide crystals are designed to catch the faint flashes of light that would occur if dark matter particles occasionally bumped into atomic nuclei. Their data shows an annual spike in June, when Earth's motion aligns with the Sun's path through the galaxy, theoretically making the dark matter wind stronger. But skepticism runs deep. Critics point out that Dama's signal could be caused by mundane factors, shifts in background radiation, temperature fluctuations, even subtle changes in the detector's environment. Other experiments like Xenon and Lux, built with different materials and methods, have found nothing. It's like two people listening for a whisper in a crowded room. One swears they heard it, while the other hears only silence. The plot thickens with alternative explanations. Could the signal come from something other than dark matter? Some theorists suggest it might be evidence of mirror matter, a hypothetical shadow world of particles that barely interact with ours. Others propose that Earth's orbit is sweeping through a clump of dark matter left behind by a long-dead galaxy, a hidden relic brushing against our detectors. What makes this mystery so electrifying is the stakes. If Dama right, we've not only found dark matter, we've mapped its flow through our cosmic neighborhood. If it's wrong, we're confronting an entirely new puzzle. Why does the universe keep teasing us with signals that vanish under scrutiny? One thing's clear: until another experiment catches the same whisper, the phantom flow of dark matter remains one of cosmology's most tantalizing maybes, a shadow just beyond our grasp. The universe has a habit of breaking its own rules, and nothing proves that quite like the Wolfe disk. This massive, fully formed spiral galaxy shouldn't exist. At least not when it did. Spotted by the James Webb Space Telescope, it dates back to just 1.5 billion years after the Big Bang, a time when the cosmos was still in its chaotic infancy. According to our best dark matter models, galaxies this size and maturity needed billions more years to assemble. Yet there it is, spinning quietly in the early universe like a grandparent at a kindergarten recital, defying every expectation. How does a galaxy like this form so quickly? Dark matter is supposed to be the slow, meticulous architect of the cosmos, gradually pulling gas and dust into clumps that eventually ignite into stars. But the Wolfe disk isn't alone. JWST has uncovered dozens of these cosmic anomalies, massive, structured galaxies lurking in the universe's toddler years. Some even show intricate spiral arms, the kind we'd expect to see only after eons of graceful evolution. It's like finding a perfectly baked wedding cake in a kitchen that just got its oven installed. Here's where dark matter's story gets messy. If these early galaxies grew without the slow gravitational dance of dark matter, what fueled their birth? One radical theory suggests that pockets of the early universe might have been seeded with ultra-dense dark matter halos, accelerating star formation at breakneck speeds. Others propose that turbulent streams of cold gas collapsed directly into disks, skipping the usual chaotic phase of galactic adolescence. But neither explanation fully accounts for the sheer number of these outliers. The real shock came when JWST peered even further back, to galaxies like Sears 93,316, which existed a mere 230 million years after the Big Bang. These celestial newborns are already packed with mature stars, challenging not just dark matter's timeline but the entire cosmic dawn narrative. If dark matter didn't shepherd their growth, what did? Could there be exotic interactions between dark matter and early radiation we haven't considered? Or is dark matter itself more dynamic than we thought, capable of rapid clustering under extreme conditions? Every new JWST image tightens the knot. These galaxies aren't just rare flukes, they're rewriting the rules of cosmic evolution. And with each discovery, we're forced to confront an unsettling truth. The universe might have had more than one way to build a galaxy. Dark matter's role, it seems, is far stranger and far more flexible than we ever imagined. So what does this mean for our cosmic blueprint? Either dark matter behaves in ways our models can't yet simulate, or something fundamental about galaxy formation remains hidden in the shadows. One thing's certain, the early universe wasn't playing by the slow, steady rulebook we wrote for it, and that's what makes this mystery so exhilarating. The Wolfe disk and its enigmatic siblings aren't just cosmic oddities, they're clues, whispering that the story of dark matter is far from complete. Imagine a cosmic freezer where dark matter comes in three flavors: cold, warm, or hot. This isn't about literal temperature, but how fast these invisible particles zip through space, shaping the universe in wildly different ways. The debate over dark matter's temperature isn't just academic. It's a battle over the very blueprint of reality, with each theory painting a radically different picture of how galaxies and life itself could have emerged. Start with cold dark matter, the reigning champion. Picture molasses in winter. Slow, sluggish particles clumping together early in cosmic history, pulling gas into dense pockets that ignited the first stars. This model, known as CDM, explains the universe's large-scale structure beautifully. Those sprawling filaments and galaxy clusters trace back to dark matter's patient gravitational pull. But there's a catch. CDM predicts a universe drowning in countless tiny dwarf galaxies, far more than we've found. Where are the missing satellites? Enter warm dark matter, the elegant compromise. Think of particles moving at a moderate pace, not slow enough to form excessive dwarfs, not fast enough to erase small structures entirely. WDM could solve the missing satellite problem by smoothing out the tiniest dark matter clumps before they birth galaxies. Some theories even suggest these particles are sterile neutrinos, hypothetical relatives of ghostly particles we already know. But warm dark matter faces its own hurdles. If it's too warm, it might struggle to explain the universe's earliest galaxies, like the Wolfe disk, which demand rapid structure formation. Then there's hot dark matter, the wild card. Imagine particles racing at near light speed, too energetic to clump on small scales. This model, popular in the 80s, collapsed when astronomers realized fast-moving particles would have prevented galaxies from forming at all. Yet remnants of the idea linger. Could a mix of hot and cold particles exist, like oil swirling in water? Or might dark matter's temperature change over time, starting hot after the Big Bang but cooling as the universe expanded? The stakes couldn't be higher. Cold dark matter favors a bottom-up universe where small structures merge into giants. Warm dark matter hints at a middle ground where medium-sized galaxies form first. And if dark matter's temperature varies, we might need entirely new physics to explain why. Simulations bring these theories to life. Cold dark matter builds intricate cosmic webs, while warm dark matter leaves gaps where dwarfs should be. The truth might lie in the shadows between them, a puzzle we're only beginning to piece together. What makes this mystery so thrilling is its reach. Dark matter's temperature doesn't just shape galaxies, it dictates the universe's rhythm. Too cold and the cosmos becomes overcrowded. Too warm and it risks emptiness. Somewhere in that balance lies the recipe for everything we see and everything we are. If dark matter is everywhere, weaving the universe together, why doesn't its gravity yank at us here in our own solar system? You'd think something making up 80% of all matter would leave a mark. Yet Earth's orbit around the Sun follows Newton's predictions almost perfectly, with no dark matter hitch. It's as if our cosmic neighborhood is a desert, parched of the invisible stuff that floods the rest of the cosmos. This odd absence is called the local dark matter drought, and it's one of the most perplexing gaps in our understanding. While galaxies like the Milky Way are swathed in vast halos of dark matter, measurements within our solar system show almost none of its gravitational fingerprint. NASA's meticulous tracking of spacecraft like the Pioneer probes and Voyagers reveals orbits matching pure Newtonian physics, no hidden mass tugging at them. Even Earth's own motion suggests that if dark matter is here, it's thinner than a ghost's whisper. So where did it go? One theory paints our solar system as a cosmic fluke, a rare bubble where dark matter was scrubbed clean. Just as some regions of the ocean have unexpected dead zones, the Milky Way might have dark matter deserts, areas where ancient collisions or gravitational jostling pushed the invisible material away. Imagine stirring cream into coffee only to find a few stubborn patches that stay black. Our solar system could be floating in one of those voids, but there's a wilder possibility. Dark matter might not be evenly distributed at all. Some models suggest it clumps into dense rivers and sparse valleys on tiny scales, meaning Earth could simply be sitting in a gully between invisible mountain ranges. If true, even a slight shift in our position over millions of years might one day plunge us into a dark matter deluge. NASA isn't giving up. Missions like the upcoming LISA gravitational wave detector could scour space for ripples caused by dark matter's subtle pull. Other proposals aim to measure Earth's acceleration through the galactic dark matter wind, hunting for fluctuations as our planet orbits. Every null result tightens the mystery, forcing us to ask, is the drought real or are we just bad at sensing the rain? The implications are staggering. If dark matter avoids our solar system, does that mean its role in galaxy formation is more selective than we thought? Or could our detection methods be missing something fundamental? One thing's certain, the quieter dark matter is here, the louder the questions become. The universe's greatest architect might be all around us, just not where we expected. Black holes, cosmic vacuum cleaners that shred stars into spaghetti, seem like the last things that could explain dark matter's ghostly presence. But what if, hidden in the chaos of the early universe, they're the perfect candidate? Imagine a swarm of ancient black holes, born not from collapsing stars but from the raw fury of the Big Bang itself. These would be primordial black holes, tiny, dense, and lurking unseen in the void for billions of years. Some theorists argue they could be dark matter, solving two cosmic puzzles at once. The idea isn't as far-fetched as it sounds. LIGO, the Gravitational Wave Observatory, has already detected collisions between black holes far heavier than expected. Could some of these be primordial relics? If so, they'd need to fit a specific profile, small enough to avoid disrupting star formation, but numerous enough to account for dark matter's gravitational grip. Picture a galaxy filled not with invisible particles, but with countless black holes, each no heavier than an asteroid, so dense that a teaspoon of their material would outweigh Mount Everest. Yet the theory has cracks. For one, primordial black holes would bend light around them like tiny lenses, a phenomenon called microlensing. Astronomers have scanned the sky for these telltale warps, but the numbers don't add up. The Milky Way would need trillions of these holes to match dark matter's mass, yet surveys see only a fraction of the expected lensing events. Even stranger, LIGO black holes are too big to fit the bill. Most primordial models require them to be lighter than the Moon. Then there's the cosmic knife edge these holes would have walked. Born in the first second after the Big Bang, they'd have had to form in a razor-thin window of density too sparse, and they wouldn't collapse, too dense, and they'd overheat the young universe, leaving scars we don't observe. It's like threading a needle across 14 billion years of cosmic history. Still, the hunt isn't over. New telescopes like JWST could spot ancient galaxies illuminated by primordial black holes feeding in the early cosmos. Others propose these holes might gather in dark matter halos, clumping together in ways that evade microlensing searches. The wildest twist, some could still be out there, drifting between stars, cold, dark, and waiting to rewrite the rules. Whether black holes solve the dark matter riddle or not, their cosmic dance forces us to rethink the invisible architecture of the universe. After all, if something as bizarre as a primordial black hole can hide in plain sight, what else might we be missing? What if dark matter isn't just an invisible particle, but something far stranger, bending the very rules of reality as we know it? Picture a cosmic fluid shimmering through higher dimensions, its ripples echoing into our universe like whispers through a locked door. Some theorists argue that dark matter's elusiveness isn't just a detection problem, it's a dimensional one. The answer might lie not in our three-dimensional world, but in the hidden folds of spacetime itself. Take quantum fluids, for example. In labs, scientists create bizarre states of matter where atoms lose their individuality, merging into a single, wave-like entity. Could dark matter behave similarly, not as discrete particles, but as a sprawling quantum ocean? If so, its gravitational pull would emerge from collective ripples, not individual collisions. It's a radical idea, but it would explain why our detectors stay silent. You can't catch a wave with a net meant for fish. Then there's the fifth-dimensional hypothesis. String theory suggests our universe might float like a sheet of paper in a higher dimensional space, with dark matter as particles that barely stick to our reality. Imagine ants crawling on a tablecloth. They sense the fabric, but not the table beneath. In this scenario, dark matter could be leaking gravity from an unseen dimension, tugging at galaxies from beyond the edges of our perception. Visualizing this gets trippy. Picture a higher dimensional dark matter halo wrapping around the Milky Way like an invisible glove. From our 3D perspective, we'd only perceive slices of it, ghostly imprints of something far grander. Computer simulations of these models reveal warped geometries where gravity behaves unpredictably, bending light into impossible shapes. It's as if the universe's hidden architect is working with tools we can't even comprehend. But here's the kicker. If dark matter is truly a quantum fluid or a higher dimensional phantom, it might not be alone. Some theories propose entire dark sectors, shadow realms with their own forces, particles, even dark chemistry. These hidden layers could interact weakly with our world, not through electromagnetism, but through some exotic fifth force. Experiments like the Large Hadron Collider are hunting for traces of these interactions, but so far, the dimensions remain stubbornly silent. The beauty of these fringe ideas isn't just their audacity, it's how they force us to rethink the boundaries of physics. Dark matter's refusal to fit neatly into our models might be the universe's way of hinting at a deeper, weirder reality. Whether it's a fluid, a higher dimensional echo, or something even more alien, one thing's clear: the truth is out there, lurking just beyond the edges of our understanding. Galaxies are supposed to wear dark matter like crowns, massive, invisible halos that keep their stars from flying into the void. But in 2018, astronomers stumbled upon a cosmic heretic, NGC 1052DF2, a galaxy that defied the rules. This faint, ghostly smudge of stars spins lazily, its outer stars moving at a crawl. No dark matter halo, no gravitational glue, just stars adrift in empty space, as if the universe forgot to dress it in its invisible cloak. The discovery sent shockwaves through astrophysics. DF2 isn't just an outlier, it's a direct challenge to everything we thought we knew about how galaxies form. If dark matter is the cosmic scaffolding, how did this structure build itself without it? One theory suggests a violent past. Perhaps DF2 was once a normal galaxy until a catastrophic collision stripped away its dark matter like a thief in the night. Picture two galaxies slamming together, their dark matter halos merging into a single blob while the stars, like stubborn stragglers, lag behind. Over eons, the stars regroup, but the dark matter never catches up, leaving a naked galaxy behind. But there's a problem. DF2's stars are too orderly, too undisturbed for such a dramatic history. No scars, no tidal tails, just serene orbits that hint at a quiet existence. This forced scientists to consider an even wilder idea. What if some galaxies form without dark matter from the start? Simulations show that in rare cases, turbulent gas in the early universe could collapse directly into stars, bypassing the need for dark matter's gravitational pull. It's like building a skyscraper without steel beams possible, but only under freakish conditions. Then came the twist. Another dark matter-deficient galaxy, DF4, was found nearby. Both live in a region dominated by the massive galaxy NGC 1052, leading some to speculate that its gravity might have siphoned away their dark matter like a cosmic vampire. Yet even this explanation feels shaky. If dark matter can be stolen so easily, why don't we see more hollowed-out galaxies? And why do these oddballs exist alongside perfectly normal galaxies in the same neighborhood? The stakes couldn't be higher. If DF2 and its kin are truly dark matter-free, they force us to rewrite the galactic rulebook. Either dark matter isn't as essential as we believed, or the universe has a secret recipe for building galaxies we've never imagined. The irony is delicious. The very stuff we thought held the cosmos together might be more optional than we ever dared admit. For now, these galaxies remain cosmic enigmas, silent rebels in a universe that supposedly runs on darkness. Every new observation tightens the mystery, leaving us to wonder, are they flukes or the first clues to a hidden chapter in the story of everything? We think we know what the universe is made of: stars, planets, gas, and dust. But here's the cosmic joke. When astronomers tally up all the normal matter, half of it is missing. That's right, even the visible universe isn't fully visible. This is the mystery of the missing baryons, the ordinary particles that should be out there, lighting up galaxies and floating between stars. Instead, they've vanished without a trace, or have they? The answer might lie in the darkest, most invisible corners of space, the warm, hot intergalactic medium, or WIM. Picture a vast, ghostly fog stretching between galaxies. A superheated plasma so diffuse it's nearly undetectable. This is where the missing baryons are hiding, scattered so thinly that spotting them is like trying to find a single drop of water in a desert. But here's the twist. Dark matter may be the reason they're there in the first place. Dark matter's gravitational pull sculpts the cosmic web, those enormous filaments of gas and galaxies spanning billions of light years. As ordinary matter, mostly hydrogen and helium, falls into these dark matter highways, it's heated to millions of degrees, becoming WIM. The catch: this stuff is so hot, it glows in X-rays, not visible light. And so sparse, even X-ray telescopes struggle to see it. It's like trying to spot steam rising from a cup of coffee from across a football field, yet the clues are there. When astronomers point X-ray observatories like Chandra at distant quasars, they sometimes find gaps in the light signs that WIM has absorbed specific wavelengths as it passes through. Other hints come from distortions in the cosmic microwave background, the afterglow of the Big Bang, which subtly shifts as it travels through these hidden rivers of gas. Slowly, we're piecing together a map of the invisible. But why does dark matter matter here? Without its gravity, the universe would lack the structure to funnel ordinary matter into these ultra-thin sheets and filaments. The WIM exists because dark matter built the highways that concentrate it. In a way, dark matter isn't just hiding itself, it's also hiding half the normal universe. Now the race is on to confirm these phantom baryons. New telescopes like ESA's Athena mission aim to scan the skies with unprecedented X-ray precision, hunting for the faint fingerprints of WIM. If we succeed, it'll solve two mysteries at once: where the missing matter went and how dark matter's invisible hand shaped its hiding place. The irony is perfect. The universe's greatest architect doesn't just build galaxies, it hides the bricks. What if dark matter isn't just sitting silently in the shadows, but secretly bustling with its own hidden activity? Picture two dark matter particles drifting through space, utterly invisible to us, yet suddenly veering toward each other as if pulled by an unseen hand. This is the wild frontier of dark matter's potential, dark force, a speculative realm where the universe's most elusive substance might not just gravitate, but communicate through forces entirely alien to our own. The idea turns conventional wisdom on its head. We've always assumed dark matter barely notices itself, its particles ghosting past one another like strangers in the night, governed only by gravity. But cosmic oddities hint at something more. Take galaxies with bizarrely offset dark matter halos, or clusters where dark matter seems to lag behind visible matter in collisions. Could these be signs of invisible interactions, tugs and pushes between dark matter particles via some exotic fifth force? Simulations let us play God with these theories, crashing dark matter together in digital universes to see what sticks. In some models, introducing even a faint dark force creates intricate structures, filaments that twist like cosmic spider silk, or halos that ripple with unseen turbulence. Imagine a parallel physics operating in the shadows. While our world runs on electromagnetism, dark matter might obey rules we can't perceive. Perhaps its particles exchange dark photons, carriers of a force that leaves ordinary matter untouched. Or maybe dark matter experiences a version of friction, slowing its motion over eons in ways that warp galaxy formation. The wildest theories propose entire dark atoms, dark protons and electrons assembling into exotic, invisible molecules. It's a cosmos within the cosmos, humming just beyond our senses. Testing these ideas isn't just sci-fi. When dark matter halos collide, like in the bullet cluster, any self-interactions would leave subtle fingerprints, smears, or delays in their distribution. Some observations already tease anomalies. A few galaxy clusters show dark matter oddly clumped, as if sticky. Yet others behave exactly as the non-interacting model predicts. The inconsistency is maddening and thrilling. Either we're glimpsing cracks in the standard dark matter story, or we're misreading the cosmic tea leaves. One thing's certain: if dark forces exist, they'd rewrite more than just astronomy. particle accelerators might someday catch whispers of these shadowy interactions, while telescopes could uncover cosmic structures sculpted by invisible hands. The search is a gamble, but as any detective knows, the most elusive clues often lead to the biggest breakthroughs. After all, the universe has never been content to play by simple rules. Why should its darkest secret be any different? Deep in the heart of the Perseus galaxy cluster, a whisper of X-ray light flickers at an energy of 3.5 kilo-electron-volts, a signal with no obvious source. This faint, unexplained glow, detected by telescopes like Chandra and XMM Newton, has haunted astronomers for years. Could it be the death rattle of dark matter itself? The idea sounds like science fiction, particles of dark matter after eons of silence, finally decaying into bursts of radiation that echo across the cosmos. But if true, it would solve two puzzles at once: the origin of these mysterious X-rays and the ultimate fate of the universe's most elusive substance. The math is tantalizing. If dark matter decays, it would do so at a rate so slow it's barely perceptible over billions of years. That fits the feeble 3.5 keV signal perfectly. Imagine a candle burning in a cathedral, so dim you'd miss it unless you stared for centuries. Yet across the vastness of galaxy clusters, where dark matter pools in unimaginable quantities, even this glacial decay could add up to a detectable glow. The kicker: ordinary matter can't produce X-rays at this exact energy. It's as if the universe left a fingerprint only dark matter could have made. Skeptics aren't convinced. Alternative explanations range from exotic plasma physics to undiagnosed instrument quirks. One leading counterargument involves sulfur ions in the cluster's superheated gas, which can emit at 3.5 keV under extreme conditions. But here's the twist: the signal appears strongest where the gas is thinnest, the opposite of what sulfur should do. It's like hearing a choir loudest in an empty room. Something's off. The stakes are cosmic. If dark matter decays even faintly, it implies an expiration date for the universe's hidden scaffolding. Over trillions of years, this slow unraveling could weaken dark matter's gravitational grip, causing galaxies to drift apart like sandcastles in a rising tide. But the real prize, decay products, would give us our first direct sample of dark matter's ingredients, a Rosetta Stone for decoding its true nature. For now, the 3.5 keV line remains a ghost in the data. Future X-ray telescopes, like Japan's XRISM mission, aim to dissect the signal with razor precision, hunting for telltale patterns that would seal dark matter's guilt. Until then, this flicker in the void stands as both a beacon of hope and a riddle wrapped in shadows, a cosmic countdown we're only beginning to hear. Among the vast tapestry of the cosmos, there are places so empty they defy logic, regions where galaxies are few and far between, and dark matter itself seems to have packed up and left. The Boötes Void is one such cosmic ghost town, a sprawling emptiness stretching 300 million light-years wide, containing only a handful of lonely galaxies where there should be thousands. It's not just an absence of stars, it's a void where even the universe's most abundant material, dark matter, appears to have gone missing. This isn't just a blank spot on the map, it's a screaming anomaly that challenges our understanding of how the cosmic web should work. To grasp how bizarre this is, picture the universe's structure like a sponge. Most of space is dense with filaments and clusters, where galaxies and dark matter clump together. Then there are the voids, the empty bubbles where matter is scarce. But even in these voids, dark matter should linger like a faint mist, its gravity subtly shaping what little matter exists. The Boötes Void, however, is different. Studies suggest its dark matter density is suspiciously low, as if something swept the area clean. Compare this to overstuffed regions like the Laniakea supercluster, where galaxies swarm in a dense, dark matter-rich knot, and the discrepancy becomes glaring. Why would the universe leave some voids barren while others hum with unseen mass? One theory points to an ancient cosmic upheaval. Billions of years ago, a titanic tug of war between dark matter and dark energy might have pushed matter out of certain voids, leaving behind near total emptiness. Alternatively, the void could be a fossil of the primordial universe, a rare spot where dark matter never clustered in the first place. Simulations show that random fluctuations in the early cosmos might have created a handful of these ultra-empty zones like air pockets in rising dough. But even these explanations feel incomplete. If dark matter is truly missing here, why don't the few galaxies inside the Boötes void fly apart? Their stars spin at normal speeds, hinting that some unseen gravity still holds them, just far less than expected. Three-dimensional maps of the large-scale universe deepen the puzzle. When astronomers chart the Boötes void alongside regions like the Sloan Great Wall, a thick, galaxy-packed ribbon, the contrast is staggering. It's as if the cosmos built a bustling metropolis right next to a desert. Stranger still, the void's edges are unusually sharp, almost as if carved out by an invisible knife. Some speculate that unknown physics, perhaps interactions between dark matter and dark energy, could have sculpted these boundaries. Others wonder if we're misreading the data. What if the void isn't empty, but filled with a form of dark matter so diffuse our instruments can't detect its pull? The stakes go beyond curiosity. If voids like Boötes truly lack dark matter, it would mean the cosmic web isn't as uniform as we thought. Dark matter's influence might wax and wane in ways that break our models. Or worse, what if our theories about dark matter's role in structure formation are missing a crucial piece? Every time we stare into these abysses, we're forced to question whether the universe's blueprint is more complicated or more enigmatic than we ever imagined. So while the Boötes void might seem like a cosmic footnote, it's actually a flashing warning sign. The same force that sculpts galaxies into glittering cities might also leave behind ghost towns, and we're only beginning to understand why. The idea that dark matter could be fuzzy sounds almost playful, until you realize it might solve some of the universe's most stubborn mysteries. Forget heavy, sluggish particles drifting through space. What if dark matter is made of something far stranger, ultralight, waves so ethereal they behave more like ripples on a cosmic pond than solid matter? This is the wild promise of fuzzy dark matter, a theory that swaps traditional particles for ghostly quantum vibrations spreading across the cosmos. Picture an ocean where every drop of water is spread impossibly thin, merging into a single, vast wave. That's the essence of fuzzy dark matter. These hypothetical particles would be billions of times lighter than even the tiniest known neutrinos, so lightweight that quantum mechanics forces them to stretch across light years, overlapping and interfering like sound waves in a concert hall. On large scales, this wave-like nature mimics the gravitational effects of traditional dark matter, holding galaxies together. But on small scales, like inside dwarf galaxies or near the centers of halos, it does something revolutionary. It smooths out. No more awkward clumps of missing satellite galaxies. No more puzzling gaps in star distributions. The fuzziness naturally erases the smallest inconsistencies that plague conventional models. The math behind this is as elegant as it is bizarre. Fuzzy dark matter particles would have a wavelength so vast that they can't cram into tight spaces, preventing the formation of ultra-dense clumps. Think of trying to squeeze an orchestra's note into a tiny whistle. It just won't fit. This automatically explains why we don't see as many dwarf galaxies as cold dark matter predicts. The waves resist fragmenting into tiny structures. Simulations show this beautifully where cold dark matter models produce a chaotic swarm of microhalos. Fuzzy dark matter leaves behind a cleaner, more refined cosmic web, eerily matching observations. But the real magic happens in the hearts of galaxies. Traditional dark matter predicts dense cusps at galaxy centers, yet many observed galaxies have soft, fluffy cores. Fuzzy dark matter's wave nature naturally disperses these cusps like a gentle tide washing away a sandcastle. Even more striking, it could explain bizarre stellar motions in some dwarfs, where stars orbit as if guided by an invisible, diffused hand rather than a concentrated mass. Of course, no theory is perfect. Fuzzy dark matter struggles to explain the earliest galaxy formation, where rapid clumping was crucial, and detecting it would require entirely new approaches, like hunting for subtle vibrations in pulsar signals or anomalies in the cosmic microwave background. Yet the elegance of the idea keeps it alive. After all, if the universe has taught us anything, it's that the truth is often weirder than fiction. So while fuzzy dark matter remains unproven, it's a tantalizing reminder that the answers we seek might not lie in heavier, stranger particles, but in the faintest whispers of quantum waves echoing through the void. 66 million years ago, a city-sized rock from space slammed into Earth, unleashing firestorms, tsunamis, and an eternal winter that wiped out the dinosaurs. But what if that asteroid wasn't just a random cosmic bullet? What if something invisible, something lurking in the very fabric of our galaxy, steered it toward us? This is the spine-chilling premise of the dark matter dinosaur extinction hypothesis. A theory so audacious it ties the fate of the dinosaurs to the hidden architecture of the Milky Way itself. The story starts with an eerie pattern buried in Earth's geological record. Fossil evidence suggests mass extinctions occur roughly every 30 million years, a cycle that suspiciously aligns with our solar system's rhythmic bobbing through the Milky Way's plane. As the Sun orbits the galaxy, it doesn't move in a flat, steady line. Instead, it oscillates up and down like a carousel horse, passing through the densest part of the galactic disk every 30 million years or so. And here's where dark matter enters the scene. Some theorists propose that a thin, invisible disk of dark matter, distinct from the galaxy's spherical halo, coats the Milky Way's midplane like a layer of phantom frost. Every time our solar system plunges through this dark disk, its gravitational jolt might disturb icy objects in the distant Oort cloud, sending deadly comets hurtling toward Earth. You can think of it as a cosmic pinball machine. Normally, the Oort cloud, a vast shell of frozen debris at the solar system's edge, hangs in fragile equilibrium. But a sudden gravitational nudge from a dense dark matter disk could destabilize it, like shaking a snow globe full of icebergs. Simulations show these disturbances might unleash comet showers, dramatically increasing Earth's odds of a catastrophic impact. It's not just the dinosaur-killing Chicxulub impactor that fits this timeline. At least 4 other major extinction events, like the Triassic-Jurassic die-off, eerily coincide with our solar system's passage through the galactic plane. But is this dark disk real? Observations of stars near the Milky Way center reveal bizarre orbital patterns, some moving faster or slower than expected, as if an invisible mass were tugging at them. A thin, dark matter disk could explain these anomalies. Unlike the galaxy's diffuse halo, this disk would be concentrated, its gravity sharp enough to jostle stars and potentially distant comets. The math is tantalizing. If just 1% of the Milky Way's dark matter settled into this disk, it'd pack enough punch to trigger periodic solar system chaos. Not everyone's convinced. Critics argue that comet showers could arise from other galactic encounters, like passing stars or molecular clouds. Others question whether dark matter could even form such a dense, flat structure without collapsing into clumps. Yet the theory's elegance is hard to ignore, a hidden celestial metronome, ticking away in the dark, shaping life and death on Earth across eons. Whether this hypothesis holds up or not, it forces us to confront a humbling truth. The universe's unseen forces might not just build galaxies, they could also, indirectly, sculpt the rise and fall of life itself. The dinosaurs never saw their doom coming, but if this theory's right, it was written in the stars, or rather, in the shadows between them. Most galaxies wear their dark matter like a heavy winter coat, thickest at the edges, thinning toward the center. But NGC 628 isn't most galaxies. This sprawling spiral, located 32 million light-years away, is practically see-through to dark matter's touch. Recent observations reveal its invisible halo isn't just faint, it's missing where it should be strongest, defying every expectation of how dark matter ought to behave. At first glance, NGC 628 looks ordinary, a pinwheel of stars spinning peacefully in the void. But when astronomers mapped its rotation curve, a graph tracking how fast stars move at different distances from the center, they found chaos. Instead of stars slowing down at the outer edges, as Newton's gravity predicts, they maintain blistering speeds without the expected dark matter scaffolding. It's like watching cars race around a track with no engine. They shouldn't be able to move that fast without something unseen anchoring them. But here's the twist: unlike galaxies like DF2, which seem to lack dark matter entirely, NGC 628's halo isn't absent. It's just redistributed. Dark matter appears concentrated in unexpected bands near the galaxy's core, then thins to near nothingness farther out, a pattern so bizarre it's been dubbed the dark matter deficit disorder. This peculiar arrangement throws gasoline on an already fiery debate. Does dark matter really exist, or are we misreading gravity itself? Enter modified Newtonian dynamics, or MUND, a controversial theory suggesting gravity strengthens where Newton's equations say it should weaken. In MUND framework, NGC 628 star speeds make perfect sense without invoking dark matter. But here's the catch: MUND struggles to explain other cosmic phenomena, like the bullet cluster's separated mass. Meanwhile, dark matter proponents argue NGC 628 might have been sculpted by ancient galactic collisions, its halo stripped and reshaped by violent encounters we can no longer see. Simulations add another layer of intrigue. When scientists modeled galaxy formation with ultra-warm dark matter particles zipping around too fast to clump tightly, they produced halos with similar patchy distributions. But if that's true, why don't all galaxies show this trait? NGC 628 might be a rare window into dark matter's quirkiest behaviors, or a sign that the universe's hidden rules are more flexible than we thought. Telescopes are now hunting for other galaxies with similar profiles, probing whether this is a cosmic fluke or a hidden pattern. Each new find forces us to confront an uncomfortable truth. The more we learn about dark matter, the less it fits into neat boxes. Whether it's an invisible particle, a glitch in gravity, or something stranger still, NGC 628 whispers that the cosmos still has secrets tucked up its sleeve. Think about the most perfectly balanced scale where every force, every particle, every flicker of energy on one side has an equal and opposite counterpart on the other. Now imagine that same symmetry applied to the entire universe, but with a twist. Everything we know, stars, planets, even light itself, has a hidden twin made of dark matter. This isn't just science fiction. It's the mirror universe hypothesis, a daring theory that suggests dark matter isn't just a lone wanderer in the cosmos, it's part of an entire shadow realm, complete with its own particles, forces, and maybe even its own laws of physics. At the heart of this idea lies a simple but radical premise. For every proton, electron, or photon in our visible universe, there could be a dark counterpart, a dark proton, a dark electron, even a dark photon mediating invisible interactions. These wouldn't just be vague imitations, they'd form complex structures like dark atoms, dark molecules, or even dark stars. Picture a galaxy where dark matter isn't just a diffuse halo but a bustling metropolis of unseen chemistry, with reactions and energies entirely alien to ours. The kicker: these two universes would coexist in the same space, overlapping like ghosts in a crowded room, yet barely noticing each other except through gravity's faint whisper. Why consider something so outlandish? Because it solves puzzles that conventional dark matter theories can't. Take the neutron lifetime anomaly, for instance. When scientists measure how long neutrons last before decaying, Experiments on Earth give one answer, while observations of space give another. A mirror universe could explain this discrepancy if neutrons occasionally slip into the dark sector, vanishing from our detectors but still leaving traces in cosmic data. Even more compelling are hints from particle colliders, where unexpected energy imbalances in proton smash-ups might be the fingerprints of dark particles carrying energy into their hidden world. But how would such a mirror universe even form? The answer might lie in the Big Bang's first moments. If the newborn universe experienced a phase transition, like water freezing into ice, it could have split reality into twin sectors, each with identical starting conditions but different rules. Over time, slight asymmetries might have allowed our sector to develop electromagnetism and nuclear forces, while the dark sector evolved its own unique interactions. Some theories suggest dark matter could even have its own version of light, not visible to us, but illuminating its own shadowy landscapes, the real challenge. Proving any of this, unlike traditional dark matter searches which look for lone particles bumping into detectors, mirror universe hunters have to get creative. Some experiments tune sensitive instruments to catch hypothetical dark photons, converting into regular photons for a split second. Others scour ancient minerals for traces of dark particles that might have left scars as they passed through Earth. And then there's the cosmic approach. If dark matter forms complex structures, its gravity could warp the light from distant galaxies in ways that reveal hidden clumps or streams. Critics argue the theory stretches Occam's razor to the breaking point. Why invent an entire shadow cosmos when one unknown particle might do the trick? Yet the mirror universe hypothesis refuses to die precisely because it's so flexible. It could explain why dark matter seems to cluster differently than predicted, why certain cosmic signals defy standard models, and even why the universe has more matter than antimatter. The deeper we look, the more the idea feels less like a wild guess and more like a missing chapter in physics' grand story. So while we can't yet peer into this hypothetical mirror, its potential echoes are everywhere. If real, it would mean our universe is just half of a far vaster, stranger reality, one where every star, every planet, every one of us has a silent counterpart moving through the dark. The thought is humbling. After all, if there's one thing the cosmos loves, it's proving we've underestimated its complexity. Why should dark matter be any different? The cosmic microwave background, the afterglow of the Big Bang, is like a fossil pressed into the fabric of the universe. But hidden in its faint glow lies a secret, dark matter's fingerprints, imprinted just moments after creation. When the Planck satellite mapped this ancient light with unprecedented precision, it didn't just capture a snapshot of the infant cosmos, it revealed how dark matter's gravitational hands sculpted reality from the very beginning. Picture the universe 380,000 years after the Big Bang. Matter and energy are a searing, opaque soup until suddenly, space cools enough for atoms to form, releasing a flash of light that still lingers today as the cosmic microwave background. But this light didn't travel unscathed. As it raced across the cosmos, dark matter's gravity warped its path like a funhouse mirror, bending and twisting it in ways that Planck's detectors could measure. These distortions, called gravitational lensing, expose where dark matter clumped long before stars or galaxies existed. It's like finding footprints in concrete that hardened billions of years ago, proof of something unseen passing through. The patterns are subtle but undeniable. Tiny temperature fluctuations in the CMB warmer and cooler spots no larger than 1/10 of a degree tell a story of early dark matter's gravitational pull. Where ordinary matter pooled, it created dense regions that would eventually become galaxies. But dark matter, indifferent to light or heat, shaped these pools from behind the scenes, its gravity amplifying certain fluctuations while suppressing others. Planck's data shows this tug-of-war in stunning detail. Dark matter's signature written in the wrinkles of spacetime itself, But here's the twist. The CMB doesn't just show us where dark matter was, it hints at what it is. The way dark matter's gravity sculpts the CMB's fluctuations rules out some theories entirely. For instance, if dark matter were hot, made of fast-moving particles like neutrinos, its gravity would have smoothed out small-scale fluctuations, leaving the cosmic microwave background far more uniform than we observe. Instead, Planck's measurements align perfectly with cold dark matter, slow, heavy particles that clump easily, seeding the universe's structure. Yet even this answer isn't perfect. Some anomalies in the data, like unexpected gaps in the CMB's polarization patterns, suggest dark matter might have played stranger, more dynamic roles in the early universe than we've modeled. Perhaps the most haunting clue lies in the CMB's large-scale asymmetries. One half of the sky shows slightly stronger temperature fluctuations than the other, a lopsidedness that defies standard cosmology. Could this be evidence of dark matter interacting with itself or with dark energy in ways we haven't imagined? Or does it point to something even more profound? That dark matter isn't just a passive scaffold, but an active participant in the universe's expansion. What makes Planck's findings so extraordinary is their permanence. Unlike galaxies or stars, the CMB can't evolve or fade. It's a time capsule, preserving dark matter's first act forever. Every new analysis peels back another layer, forcing us to confront how little we truly understand about the force that built the cosmos. The echoes are all around us, etched into the oldest light there is. We just have to learn how to listen. We've always imagined dark matter as slow, lumbering giants, vast clouds of heavy, sluggish particles drifting through space. But what if that's completely wrong? What if dark matter moves at speeds approaching the cosmic speed limit, velocities so blistering they brush against the edge of light itself? This is the mind-bending premise of relativistic dark matter, a theory so radical it rewrites the timeline of the universe's construction. Most models assume dark matter is cold particles moving at a snail's pace, allowing them to clump together easily under gravity's pull. But simulations incorporating fast dark matter particles zipping through space at a significant fraction of light speed paint a wildly different picture. Imagine trying to build a sandcastle in a hurricane. High-speed dark matter would resist clumping on small scales, smoothing out the universe's structure like a cosmic iron. Yet somehow, against all odds, galaxies still formed, and faster than traditional models predict. The speed of dark matter isn't just a technical detail, it's a cosmic clock. If dark matter moves too quickly, it could have delayed galaxy formation by billions of years as particles streamed freely through space, resisting gravity's pull. But that's not what we see. Observations of the earliest galaxies, like those spotted by the James Webb Space Telescope, reveal fully formed celestial cities when the universe was barely a toddler. Vast dark matter shouldn't allow this, unless, of course, we've misunderstood how it interacts with itself. Some theorists propose a compromise. Dark matter might have started hot and relativistic, then cooled as the universe expanded. Picture a pot of boiling water gradually settling into stillness. This would allow rapid initial expansion, followed by the gradual formation of structure matching both the early galaxy problem and the universe's large-scale web. Others suggest dark matter could have multiple flavors, some fast, some slow, blending together to sculpt the cosmos in phases. The implications ripple outward. If dark matter is relativistic, it might explain the scarcity of dwarf galaxies, their small size making them vulnerable to disruption by high-speed particles. It could also alter our understanding of dark matter detection. Current experiments are tuned to catch slow, heavy particles, but if dark matter is racing past at near light speed, we'd need entirely new methods to trap it. The most thrilling possibility, relativistic dark matter might not be entirely dark. Some models suggest these fast-moving particles could occasionally collide, sparking bursts of gamma rays or other high-energy signals. Telescopes are already scanning the skies for such flashes, potential smoke from dark matter's invisible fire. Whether this theory holds or not, it forces us to confront an exhilarating truth. The universe's greatest mystery might not just be hidden, it could be hurtling past us at unimaginable speeds, leaving behind only questions in its wake. What if dark matter isn't just an invisible cosmic scaffold, but something far stranger, something alive? Not in the way we think of life, but in a way that challenges the very definition of consciousness itself. This isn't just wild speculation. It's a fringe theory that ties dark matter to one of philosophy's most mind-bending ideas, panpsychism, the notion that consciousness isn't exclusive to brains, but is a fundamental property of the universe woven into the fabric of reality. And if that's true, could dark matter be its silent carrier? Picture this: every particle of dark matter, every invisible wisp of this enigmatic substance, might possess a faint glimmer of experience. Not thoughts, not emotions, but a primal, rudimentary awareness, like the barest whisper of subjectivity humming through the void. In this view, dark matter isn't just passively holding galaxies together. It's the universe's deepest, oldest layer of sentience, a vast network of proto-consciousness stretching across billions of light years. It sounds like science fiction, but some theorists argue it solves two mysteries at once: why dark matter seems to evade detection, and why consciousness exists at all. The logic, if you can call it that, goes like this. If consciousness is as fundamental as space or time, it needs a substrate, a medium to propagate. Ordinary matter, the stuff of stars and brains, is too chaotic, too volatile. But dark matter, stable, pervasive, and utterly indifferent to the noisy interactions of light and atoms, it's the perfect cosmic canvas for a silent, slow-motion dance of awareness. Think of it like the ocean, where the waves crashing and frothing with individual thoughts, while dark matter is the deep, still water beneath, a reservoir of latent sentience. Now, before you dismiss this as cosmic fantasy, consider the eerie parallels. Dark matter's gravitational influence shapes galaxies much like consciousness shapes perception, organizing chaos into structure without leaving a visible trace. And just as we can't directly observe another mind, only infer its existence through behavior, we infer dark matter through its gravitational shadow. The similarities are tantalizing, but are they meaningful? Skeptics rightfully point out that this is less a testable hypothesis and more a poetic metaphor. There's no experiment to prove dark matter feels, no instrument to measure cosmic qualia. Yet the idea persists, fueled by psychedelic experiences where users report sensations of merging with a vast, interconnected awareness, as if brushing against the universe's hidden mind. Could these fleeting glimpses be encounters with dark matter's subtle influence, or are we simply projecting human longing onto the cosmos? Either way, the theory forces us to confront a profound question. If consciousness emerges from matter, why couldn't it emerge from all matter, even the kind we can't see? Whether you buy into this or not, the sheer audacity of the idea is electrifying. Dark matter might not just shape galaxies, it could be the universe's silent witness, a sentient shadow watching from the edges of reality. And if that's true, then every time we look up at the night sky, we're not just staring into the unknown. We're staring into something that might, in some unfathomable way, be staring back. We think of dark matter as eternal, a silent, unchanging spectator that's lingered since the dawn of time. But what if it's not? What if, like everything else in the universe, dark matter has a life cycle, a birth, a transformation, even a death? This isn't just philosophical musing. It's a radical shift in how we view the cosmos's hidden architect. If dark matter decays, evaporates, or mutates over eons, it could rewrite the fate of everything from galaxies to the universe itself. Take the 3.5 kilo-electron-volt X-ray signal from galaxy clusters, the tantalizing whisper we discussed earlier. If that's truly dark matter decaying, it implies a clock is ticking. Even at a glacial pace, decay would mean dark matter's dominance isn't permanent. Picture an hourglass floating in deep space, its grains of invisible sand slipping away one by one. Over trillions of years, that slow unraveling could weaken dark matter's gravitational grip, causing galaxies to drift apart like smoke in the wind. Stars would still burn, planets would still orbit, but the cosmic web, the grand design dark matter sculpted, would fray at the edges, leaving the universe a dimmer, lonelier place. Yet decay isn't the only possibility. Some theories suggest dark matter might transform instead of vanishing. Imagine an ice cube melting into water, its essence preserved but its form altered. Could dark matter particles shift into something else, lighter particles, or even exotic energy? In certain models, this metamorphosis could explain why the universe's expansion is accelerating. As dark matter converts into a new state, it might release energy that nudges galaxies apart, adding fuel to dark energy's mysterious fire. It's a cosmic feedback loop. Dark matter shapes the universe, then the universe's expansion reshapes dark matter. The wildest twist, dark matter might not even be a single substance. Just as stars evolve from hydrogen-burning youth to white dwarf senescence, dark matter could have generations. Early in the universe, it might have been hotter, faster, more dynamic particles colliding and annihilating in bursts of hidden radiation. Over time, as space stretched and cooled, those particles could have settled into the sluggish, cold dark matter we infer today. Telescopes probing the cosmic dawn might already be catching glimpses of this primordial dark matter in action, its fingerprints etched in the formation of impossibly early galaxies. But how do we test these ideas? Particle colliders are hunting for signs of dark matter's demise, like subtle imbalances in energy after smash-ups that hint at invisible decay products. Astronomers, meanwhile, are comparing galaxy clusters of different ages, searching for evidence that dark matter's influence wanes over cosmic time. Even gravitational wave detectors could play a role if dark matter decays into hypothetical particles called actions. Their ghostly vibrations might warp spacetime in telltale ways. The implications are staggering. If dark matter has a life cycle, then the universe we know is just a phase, a fleeting moment in a much grander story. Structures we consider permanent galactic superclusters, the cosmic web, might be temporary sculptures in an ever-shifting dark landscape. And that raises a haunting question. If dark matter can change, what else about our cosmic rules isn't as fixed as we thought? One thing's certain, the universe doesn't do immortality. Stars burn out, black holes evaporate, even protons might someday decay. Dark matter, it seems, is no exception. Whether it fades, transforms, or rebirths itself into something new, its story is far from over, and we're only beginning to read the first page. For over half a century, dark matter has reigned as cosmology's go-to explanation for the universe's hidden mass. But what if we've been chasing a ghost while the real answer was hiding in plain sight, written into the very laws of physics themselves? This is the radical proposition of modified Newtonian dynamics, or MUND, a theory that dares to ask, could our understanding of gravity itself be incomplete? MUND's premise is deceptively simple. Instead of invoking invisible matter to explain why stars on galaxy outskirts move too fast, it tweaks Newton's second law at extremely low accelerations, the realm where gravity grows faint. Picture a car slowing as you ease off the gas. Normally, deceleration follows predictable rules unless, say, your brakes behave differently at creeping speeds. MUND suggests gravity similarly misbehaves, where its pull becomes weak, strengthening just enough to account for those runaway stars without dark matter's help. It's not a wholesale rewrite of physics, but a subtle edit, one that remarkably predicts galaxy rotation curves with uncanny precision. The theory's elegance is seductive. Unlike dark matter models, which struggle with quirks like the Milky Way's sparse dwarf galaxies or NGC 628's bizarre mass distribution, MUND handles these anomalies naturally. Its equations spit out flat rotation curves automatically, no invisible halos required. Even more compelling are predictive winds cases where Mund forecasted galactic behavior before telescopes confirmed it. When astronomers discovered stars in isolated galaxies moving faster than dark matter models allowed, Mund had anticipated the result years prior. Yet for all its triumphs, Mund faces brutal hurdles. The Bullet Cluster remains its nightmare scenario. When two galaxy clusters collided, their visible gas piled up at the center, while the bulk of their mass, revealed by gravitational lensing, sailed ahead unimpeded. Dark matter explains this beautifully. Its particles, oblivious to collisions, carried the cluster's gravity with them. Mund, lacking invisible mass, strains to account for the separation. Theorists have proposed tweaks like positing unseen neutrino clouds, but these feel like ad hoc fixes, undermining the theory's initial simplicity. Then there's the cosmic web. Dark matter's sluggish particles perfectly explain the universe's vast, galaxy-strewn filaments. Mund struggles to replicate this structure without invoking, ironically, some form of unseen matter. Even its staunchest advocates concede it may need extra ingredients to match large-scale observations, blurring the line between Mund and dark matter hybrids. The debate intensifies with quantum gravity theories. Some versions of string theory and loop quantum gravity suggest space-time itself might have granular properties that subtly alter gravity's behavior on cosmic scales. These ideas remain speculative, but they hint at a possible middle ground. Perhaps gravity's laws do shift in ways we don't yet grasp, while dark matter also exists in some form. What makes this mystery so electrifying is its stakes. If Mund is right, we've spent decades constructing an elaborate fantasy to explain what a single equation could have solved. If wrong, its very existence reminds us how much we still don't understand about gravity's whisper-thin tendrils. Either way, the universe seems determined to humble us, revealing that our cosmic maps, whether drawn in dark matter or modified equations, still harbor uncharted territory. The real breakthrough may come when we admit both theories could be simultaneously incomplete, and that the truth, as always, lies just beyond the edge of our vision. From ghostly galaxies missing their dark matter to whispers of X-rays that might be its dying breath, we've journeyed through 25 of the cosmos' most baffling enigmas, each one peeling back another layer of the universe's greatest secret. And yet, after centuries of searching, dark matter remains as elusive as ever. We've mapped its shadow through spinning galaxies, watched it shrug off collisions in the Bullet Cluster, and even wondered if it's a silent witness to the rise and fall of life itself. But for every answer, a dozen new questions erupt. Why does it vanish in some galaxies but dominate others? Could it be whispering to us through higher dimensions, or is it an entire mirror universe brushing against ours? The deeper we dig, the more we realize how little we truly know. This isn't just a scientific puzzle, it's a humbling reminder that the universe loves to defy expectations. Dark matter doesn't just hide in the shadows, it rewrites the rules, bending reality in ways we're only beginning to grasp, and that's what makes this hunt so thrilling. Every failed experiment, every anomalous galaxy, every flicker of unexplained light isn't a dead end. It's a signpost pointing toward something stranger, something we haven't even imagined yet. So now it's your turn. Which of these mysteries keeps you up at night? Is it the phantom galaxies that defy gravity's rules, or the eerie possibility that dark matter could be decaying all around us? Maybe you're captivated by the idea of a hidden cosmos, or the chilling thought that dinosaurs were wiped out by an invisible cosmic force. Whatever it is, let's keep the conversation going. Drop your thoughts in the comments, because the next big breakthrough might just start with a spark of curiosity. After all, the universe's greatest secrets aren't meant to be solved alone. They're waiting for all of us to piece them together, one mind-bending mystery at a time.